changes mediums, that affects the speed. So it's always going to be slower than the speed of light in a vacuum because that's like the fastest it can possibly travel.
Very nice.
So when you have like the center line, the normal line,
Yep.
then if it comes in at an angle and then slows down, the part that slows down will be closer to the normal.
Okay, can I interrupt you for a second? So you've covered a lot, and I want to take it a little bit more slowly than that. So before we get to the point about the changing of wavelengths, could we talk a little bit about just what the index of refraction tells us? So you said it's related to how much something slows down when it goes from vacuum to some material. Okay, correct? Okay, so Ella, this ratio has some mathematical constraints based on the laws of physics. What's the deal with this ratio? Okay, say that again?
It has to be.
It has to be bigger than 1 because, why?
Because it's the ratio.
Because the speed of light in a vacuum is always greater than the speed of light in some material. In other words, the speed of light in any material is always less than the speed of light in a vacuum. Light only slows down when it goes from empty space to stuff. Okay, it never speeds up. In fact, believe it or not, this is a cosmic speed limit placed on all material and immaterial objects. Okay, stuff doesn't go faster than c. Nothing goes faster than c. So the index of refraction always has to be greater than 1. Cool. Okay. So you started to talk about wavelength. Could somebody tell us a little bit about wavelength? So we know.
Well, the wavelength gets shorter when it passes into a new medium
Okay.
because the speed decreases. So if you took the formula, the frequency is the same. So if the speed decreases, then the wavelength has to decrease.
You mean this formula?
Yeah.
Could you say that again? That's totally correct.
Okay. The frequency always stays the same, so you can like kind of cross that out of the equation.
Mm-hmm.
And so if the speed, if the thing on the left decreases, and the thing on the right has to decrease also.
Nice. Why does the frequency stay the same?
Because that's like a defining characteristic of the type of light. So it's
Got it.
that always just.
Yeah, so I like the way you say that. It's a defining characteristic of the type of light, okay? And interestingly, like that's the physical thing that's at play here. In other words, the light kind of wiggles through space and then it hits this air-water boundary or this air-glass boundary. And it is the frequency of tapping on the boundary that's responsible for propagating the wave into the new stuff. So the frequency has to not change because it's the characteristic thing. Therefore, the speed of light in the medium as it drops has to decrease the wavelength, okay? Okay, so if that's true, this is how we sort of require that the light ray will bend if it's incident at a non-zero angle. In other words, this decrease in wavelength because of the constant frequency is what makes the light wave bend. What was the deal with that? Does anybody remember?
That's because like one, I guess, side of the wave decreases the speed before the other side, I guess, and then that's what causes it to slow down in one part of the wave, and that's why it bends.
Great. Yeah, and I think the essence of that was that the wave fronts themselves are not allowed to break. They're not allowed to be sort of discontinuous. They have to like be continuous, and then bending is what makes all of this possible. What's the one angle where you don't get bending?
Straight.
0 degree incidence. 90, with 0 degrees relative to the normal, right? Okay. And I think we also saw that the steeper your incident angle, the more bending you expect. Okay, and there were lots of fun things we did with lasers the other time and all of that. Okay, so here's my normal line. going to call this my incident ray, like such. I'm going to say that this is my refracted ray, like such. Okay. And I'm going to draw some wave fronts that go with these light rays. So what's the deal with wave fronts relative to light rays? Camille?
They're perpendicular.
Nice, they are perpendicular. Good. So, and that's just sort of the abbreviation that we make when we talk about light rays. So here we go with our perpendicular waves. This guy is something like that. And then maybe that. And then maybe that.
Pretty good. Yeah, pretty good.
So far?
No,
Okay.
that's actually okay.
Thank you. And then for this one, perpendicular to the refracted ray, we'll say, what do you think on it? No?
I think it's good. There.
Okay. And so on. So what I'd like to do is I'd like to get you thinking a little bit about some of the rules of geometry as they apply to this problem. Okay? Here's what I mean by that. So let me just remind you that, see that angle there? That's my incidence angle. I'm going to call that theta 1. Okay, and so see this angle here? That's my refraction angle. I'm going to call that theta 2. Just for completeness, let me just remind you we're going to call this index of refraction N1, could be air. We're going to call this index of refraction N2, could be glass or water. Okay. There's a couple of triangles here, though, that I'd like to point out for you. Okay, so first of all, there's this triangle. Okay. And second of all, I can see this dotted line that I'm drawing. I can draw that dotted line because that dotted line is the one that's parallel to the light ray. So that's legal for me to do. And I've just created a second triangle that looks like this. Okay? Those two triangles share some characteristics, so I'm going to make them larger. Okay. I'm going to make those triangles larger. Okay. I hear some recognition, and that's great. So let me draw those triangles much bigger. Here's that. Oh, jeez. Sorry, Anna.
Okay. Okay.
Okay, so that's 90 degrees. I think I just made that worse, didn't I?
Yeah.
It doesn't matter.
It matters.
It does matter.
Okay, 90 degrees.
Triangles get worse every time you read it.
Okay, that's my 90 degrees. See my shaded line here? That's the shared side of the two triangles. And then the triangle that I had on the bottom was this one. Okay? I know, all right.
No.
Just retrace the same.
You squint and it's not as bad.
Okay.
Just
pretty bad, actually.
Are you all aware that this is my theta 1?
Yes.
Okay. If that is my theta 1, it's not too complicated to show that that is theta 1. Okay?
Wait.
So let me say that again. It's not too complicated to show that this is theta 1 if that is theta 1. All right? I'm going to give you a really simple physical argument for that, and then I'm going to ask you to prove it geometrically, not with the formal proof. But watch this. See my normal line and my wavefront line? Okay, you ready for this? If I tilt away from the normal line by an amount of theta 1, can you see that I've also intersected the horizontal by theta 1? Okay. Another way to prove this, pretty straightforwardly, is that the sum of the interior angles is 180. Okay. This is a right angle, which makes this 90 minus theta 1. So we've got 90 minus theta 1, 90, and then x. Okay, therefore x must be theta 1. Okay. Let's do the bottom triangle. if my light ray were to bend down to here, this is my theta 2, okay? It shouldn't be too complicated for you to see that in my triangle, that this is theta 2. I'm going to give you a really good physical way to see that. See my normal line here? And my boundary, this top ruler is like my boundary. If I tilt up like that, you can see that I've tilted away from horizontal by the same angle. Okay, this is my away from horizontal. That's my away from normal. They're the same angle. Okay? All right. Anybody want to prove that geometrically?
No.
Oh, come on.
Oh no, the base. Oh, okay. The base like of theta 2 and the 90 degrees. That
Mhm.
base right there,
Yep.
and the other one that goes
Okay.
down there. That makes 90 degrees.
Good.
And then the space in between is 90 minus theta 2, and then.
Nicely said. Point being, that's theta 2, that's theta 1. Okay, now, these triangles have to be congruent because they share a side and they also share an angle, right? 90-degree angle,
That's just side angle.
right?
That's so you did
Because you already
something
know.
else.
Don't you need another thing? You need a third.
Sorry, did I say congruent? I meant to say proportional.
Okay.
Sorry, my mistake. These triangles are proportional. Right? Now, I just wanted to also interject a little bit of physics here. This length is something physical. Does anybody remember what this length is? What does this length represent?
The wavelength.
That's the wavelength. That's my lambda 1.
Oh.
Okay? This is my lambda 2. Okay?
That's hella big.
Also, you might recognize that I've got something called a right triangle here. My right
Wait, how do
triangle.
you know that?
My right triangle. I'm gonna define something called the ratio of. You guys ready for this? Okay. So look at my theta 1. If you look opposite the triangle, you're looking at lambda 1. The ratio of lambda 1 to the hypotenuse is called the sine of theta 1. That's the definition of the sine.
So lit.
Okay?
Oh, that's what the sign does.
Yes. Now, in this triangle, if you are theta 2 and you look across the triangle, the opposite side to you is lambda 2. The ratio of lambda 2 divided by the hypotenuse is the sine of theta 2. Okay?
Yo.
Okay, check it out. See how these two things share a side? That's the same hypotenuse for both triangles. Okay? So I'm going to solve this equation for 1 over the hypotenuse. Okay, 1 over hypotenuse is equal to lambda 2 divided by the sine of theta 2. Did you guys see that? Pretty simple algebra right there. I'm going to take this equation and I'm also going to solve it for 1 over hypotenuse.
I don't think that's 1 over hypotenuse. It's just hypotenuse.
Oh, sorry. My mistake. Thank you. 1 over hypotenuse is sine theta 2.
Well, you erase it on part.
No, I want to keep it that way.
No, like there's no 1 over
Yeah, there
for hypotenuse.
He made
Because you multiply both sides by hypotenuse and then you divide it.
is. He redid it. He just
What do you mean?
he redid it because he wants to keep it like
He
that.
wants it 1 over hypotenuse.
Oh, I see. I didn't see the flip. I didn't see the
Okay. Good? Okay. So everybody I hope sees that sine theta 2 over lambda 2 is that. Sine theta 1 over lambda 1, excuse me, is that. These two things equal the same thing, so they must equal one another, right? Let me say that again. Those two things equal the same thing, so they must equal one another. So sine theta 1 over lambda 1 equals, hold on, sine theta 2 over lambda 2. Oh, we're getting close to something.
Oh, so the ratios are equal.
Very nice. The ratios are equal. But actually, Jackson, I'm videotaping this whole thing.
Yeah, I know.
So,
But like,
okay.
I don't want to have to look through the
Does
whole
anybody remember this thing called the index of refraction and how It's what scales the wavelength. Okay. So I'm wondering if anybody could make the final leap from this statement to the law of refraction. Okay. So let me say that again. Joshua, you want to add something? What do you think? What do you think?
Well, since we know that the ratio of the wavelength 1 and wavelength 2 is n1 to n2,
Mm-hmm.
and we have a proportion, we can replace it, right?
So since n1 is to n2 is equal to the ratio of lambda 1 to lambda 2, good. This is, by the way, from last week's notes. You can look that up. So yeah, take me through it.
So we can do sine theta 1 over n1.
Can we say sine theta 2 for right now?
Yeah, sorry.
And what?
n1 over n2.
Is it maybe n2 over n1? I think actually this is flipped.
Oh, right, yeah.
Yeah.
And then
Cross multiply
multiply, and we get, yeah.
the law of refraction. Okay. So can I make a quick observation here? The law of refraction involves something called a sine function. Really what we're talking about here is the ratio of, okay, listen carefully, how the wavelength scales based on the index of refraction as the thing that forces the angle to be what it is. Okay, let me say that again. You do not need to know how to derive the law of refraction. Okay, you don't need to know how to derive that. But you do need to understand that the sine of the angle is not magically invented out of thin air. Okay, it means something. What it means is that the fact that the wavelength gets shortened by this amount due to the slowing down of light is what drags the angle over by a proportional amount. Okay? And what's fixed here is the boundary, and so that's the thing that sets the ratio. Okay? Okay, so that's the derivation of the law of refraction. How do we prove it by experiment? What things could we do? What things could we measure? And then what things do you think we could look up to see if we got the right answer? Maybe that's not a great question. Good. Jackson, go for it.
You could determine what the speed of a light of an object is,
Okay.
and then Google it.
Okay, so we could determine the speed of light in an object and then Google it. We could also determine the index or refraction of an object and then Google it. When you say Google it, what you mean is you look up the accepted value.
Yeah,
which is,
that's what I
yeah.
meant.
Okay. Ella? Okay. So how do you think we can get the index of refraction? Sorry, I know I have a lot of boards going on here. Okay, how do you think we can get the index of refraction? So we have this thing we're claiming is true. We have a mathematical claim that this is a true statement. We're going to prove this by experiment. That's what physics is. Physics is about looking for data that agrees with a mathematical model. There's our math model. What do you think the best way to validate this math model might be? Say that again?
Test it.
I mean, tell me about an experiment.
Oh, no.
Go.
Couldn't you put a ray of light through a material and measure the angle that goes in and the angle that goes out, and then
Great.
find indices?
Great.
Yeah.
Index, yeah. Okay. So what Roxy is saying is you measure the angle of incidence of a light ray, and then you measure the angle that it refracts in a new material and see if it works. You could then calculate the ratio of the sines of those angles and get the index of refraction. Let me say that again. What Roxy is basically saying is that if you measure theta 1 and you measure theta 2, you can then put them into your calculator and expect that the ratio of this to that is the ratio of this to that. Okay? So here's how we're going to do this. We're going to plot the sine of theta 1 on a y-axis. And then we're going to plot the sine of theta 2 on an x-axis. What should the data look like, and what should the slope be? Say that again. What should the data look like, and what should the slope be? Okay, go ahead.
I think it should be linear.
Mm-hmm. You are totally correct. And what would the slope be?
1. Sine theta 1.
If you solve this equation for sine theta 1 over sine theta 2, see how?
Wait, would it be the index of refraction?
It absolutely would. Okay, the slope of this data set is going to be, and which one is it, Sienna? Is it N2 or N1? Or both?
Wait, isn't it the ratio of?
It is. It's N2 over N1. But the index of refraction of air is basically 1. It's like 1.000 something something. It's a very, very close to 1 value. So the slope is going to be the index of refraction of our material. Okay, and this is the best way to determine the index of refraction of a material is by finding the slope of this data set. It's complicated, right? Do you remember how easy the law of reflection was? And we were like, oh yeah, incident angle, reflection angle, just plot them in as linear. Now we need these, but if you think carefully about what this is even saying, we're talking about the ratio of the wavelengths, more or less, and the sign helps us calculate that. It's not too uncomfortable to think that this should be a linear data set, the slope of which is N2. Okay? So, how are we going to do that? Well,